time. So in this next section, we left off talking about molar mass and calculating the molar mass for different molecular species. Now we're going to talk a little bit about a central unit that is utilized in chemistry to talk about groups of atoms or molecules known as the mole. Now, we know from our previous experience that the mass of atoms and molecules are small, on the order of 10 to the negative 24th grams. Since we handle quantities on the scale of grams, we look rather at a single atom, we instead look at a group of atoms or a group of molecules. Now, to help us understand this analogy, we count eggs in dozens, right? This is a unit of counting. A dozen implies that we have 12 things per dozen. So for example, if we have 1 dozen atoms, we would have how many atoms? So if we said we had 1 dozen atoms, we would have how many atoms? What does a dozen represent?
12.
Well, exactly right. By the same token, if we have 4 dozen molecules of water, this would correspond to 48 molecules of water. Okay, so we can use a dozen to describe a group of atoms. Okay, now if we're counting very large numbers of objects, we count the moles of objects. Now, just like a dozen represents 12 things, a mole represents 6.02 times 10 to the 23rd things. So for example, a mole of atoms would represent 6.02 times 10 to the 23rd atoms. A mole of molecules would represent 6.02 times 10 to the 23rd molecules. So this number, 6.02 times 10 to the 23rd, is known as Avogadro's number, which is a common constant utilized in chemistry. Now, one thing that's really useful about the idea of a mole is that if we think about the mass in terms of AMU per atom, if we wanted to convert the mass in AMU per atom into the mass in gram per mole, we can develop a relationship between the molar mass written in AMU per atom and gram per mole using unit conversions. So we can write this as gram per atom, and then finally gram per mole, just a two-step conversion. Now, we're not too concerned with the mechanics behind this conversion. So for example, let's say we're looking at hydrogen, which is a mass of 1 AMU per atom. The point that I want you to take away from this next discussion is that we can show that the molar mass in gram per mole in the periodic table is about equal to the molar mass in AMU per molecule. So let's show that. So for hydrogen, for example, if it's 1 AMU per atom, we know that there are 1.67 times 10 to the negative 24th gram per AMU. And we know that we have 6.02 times 10 to the 23rd atoms per mole. And if we punch this into our calculator, we get about 1 gram per mole of hydrogen atoms. So the main thing that I want you to take away from this is that reading the periodic table, when you see something like hydrogen or any other element in the periodic table, you can read your atomic mass you can read your average atomic mass in gram per mole or AMU per atom, with the units of gram per mole being far more common and useful in chemistry calculations, because we naturally handle materials on the scale of grams. Does this make sense to everyone so far? So a mole serves as a way to count groups of atoms. And we can look at the mass of a mole of atoms, and that in turn is our molar mass. Any questions so far? Any questions so far? Is everyone comfortable with this idea so far?
Yeah, so 1 mole is equal to the molar mass in
So
AMUs.
so a mole represents a large number of atoms. One consequence of this is that we can look at the mass of a mole of atoms and the molar mass. So the molar mass can either be written as AMU per atom or gram per mole. And this gram per mole unit for molar mass is far more useful in a lot of common chemistry calculations. Does that make sense?
Yes, thank you.
Perfect. So let's talk about some mass to mole conversion. So I've made this little chart that can help you execute on mass to mole conversions. So let's start off on this right-hand side here. To go from moles to mass, we use our molar mass. That's our conversion factor. So to go from moles to mass, we would multiply by our molar mass. To go from mass to moles, we would divide by molar mass. You don't necessarily have to memorize this process, because if you look at the units, you can treat these problems like a simple unit conversion problem. The units really are your guide to solving these problems. So let's look at an example. We're asked how many moles of iron are in 33.0 grams of iron. So first I need to go to the periodic table and look up iron. Would someone like to tell me what is the molar mass of iron? What is the molar mass of iron?
55.85.
Okay. Yep. And what would the units be? What would the most useful units be for the molar mass for this problem? If we're starting with grams and we want moles, what units should this molar mass have?
Gram per mole.
Yep, exactly right. Perfect. So now that we have our molar mass, so we're trying to go from grams of iron to moles of iron. So if we have 33.0 grams of iron, if I want to go from grams to moles, what should be on top in our conversion factor? What should be on top? If we're going from gram to moles, then moles should be on top. Exactly right. And in 1 mole of iron, we know that we have 55.85 grams. Okay, so now all we have to do is punch this into our calculator. So let's enter this into our calculator. So we have 33 divided by 55.85. And that in turn gives us 0.59086 moles of iron. We then round our answer to 3 sig figs, which gives us 0.591 moles of iron. Does this make sense to everyone? Any questions on this example? So we're applying this idea of molar mass in gram per mole to convert between the grams of a sample and the moles of atoms or molecules in that sample. Any questions on this part? Any questions? Okay, so let's look at another example. Let's look at another example. This time we're dealing with a molecule. Okay, we're asked what mass of carbon dioxide is found in 1.55 moles of carbon dioxide. Okay, so we're trying to go from the moles of carbon dioxide to the grams of carbon dioxide. And what conversion factor do we need? What conversion factor do we need?
Mole per gram.
Yep, exactly right. So we need, rather than the atomic mass, we need the molar mass of carbon dioxide. And we can calculate that. So let's look up in the periodic table carbon and oxygen. What is the atomic mass of carbon? What is the atomic mass of carbon? What is the mass of carbon noted in the periodic table?
12.01.
Yep. And then oxygen is 16.00. So if we want to calculate the molar mass of carbon dioxide, the molar mass of carbon dioxide would be the mass of carbon, which is 12.01 gram per mole, plus the mass of oxygen, which is 16.00 gram per mole, times 2. That gives us, for our molar mass of carbon dioxide, 44.01 gram per mole carbon dioxide. Remember, we talked about this molar mass and molecular mass calculation last class session. The only thing that's new is we're using the masses in gram per mole. Does this make sense to everyone so far?
Yes.
Perfect. So to go from moles of carbon dioxide to grams, I'm going to plug in my initial moles of carbon dioxide. And to go from moles to grams, if I'm going to grams, I'm going to need grams on top. So we have 44.01 grams of carbon dioxide per 1 mole of carbon dioxide. The units of moles cancel. And now punching this into our calculator, we in turn get 68.215 grams of carbon dioxide that we round to 68.2 grams of carbon dioxide. Does this make sense to everyone? Any questions on this example? So if I don't see any questions, let's make sure that we're comfortable with this idea, and let's work on the following set of examples where we're asked to execute mass to mole conversions. So I'd like you to work on these examples over the next 4 to 5 minutes. I'd like you to tell me what mass of carbon is found in 2.5 moles of carbon, and how many moles of benzene are found in 156 grams. So let's work on these examples over the next 4 to 5 minutes. And don't be shy to share your questions or your proposed responses in the chat or verbally. And I'd be happy to provide feedback on any proposed responses that you submit in the chat or verbally. And if you have any questions, again, don't be shy to ask. You're also more than welcome to share your work using the annotate tool if you're feeling inclined to that. So let's work on these examples, and I'd like to see a pool of student responses for each question before we discuss. And again, don't be shy to share your proposed responses in the chat or verbally, and I'd be happy to provide feedback. And if there are any questions, really don't be shy to ask. And don't be shy to propose an answer that necessarily disagrees with your classmates. The more responses we have, the more we can have a nuanced discussion. And we'll talk about these examples in another 2.5 to 3 minutes. And it's nice to see a range of responses from the class. The responses are well formatted so far. I greatly appreciate that both the number and the exact units are specified. Let's try to get a few more responses. And if anyone has any questions on this, really don't hesitate to ask. We're going to be building up and building on these simple conversion steps in order to handle more complicated unit conversion problems. And we'll discuss this example in about another minute. Don't be shy to share your responses in the chat. I greatly appreciate the students who've shared their responses in the chat, and really don't be shy. And if you don't want to type in the chat, in the public chat, you can also message me your responses in the private chat, and I'd be happy to look them over and provide feedback. So let's talk about this example. We're asked what mass of carbon is found in 2.5 moles of carbon. So let's set up our solution map. We are trying to go from the moles of carbon to the grams of carbon. We know from the periodic table, carbon has a mass of 12.01 grams per mole. So if we have 2.50 moles of carbon, and just as a side note, based on this, I really want you to specify your units, not just moles, but moles of carbon. And that's so that way we keep things perfectly organized when we start to deal with mole to mole conversions. So if we have 2.5 moles of carbon, we multiply by our molar mass, which is 12.01 gram per mole. So 12.01 times 2.50, that in turn gives us a mass of 30.025 grams that we immediately round to 30.0 grams to respect that our input has a total of 3 significant figures. Does this first question make sense? Does this first question make sense? Overall, all of the responses I got in the chat for this first problem were perfect. Let's look at this next case. We're asked how many moles of C6H6, which is benzene, are there in 156 grams? So first we need to calculate the molar mass of C6H6. So we take the mass of carbon, which is 12.01 gram per mole of carbon. We know that we have 6 carbons. We then take the mass of hydrogen, which is 1.00 gram per mole of hydrogen, and we multiply by our number of hydrogens. Punching that into our calculator, that gives us a mass of 78.06 grams per mole of C6H6. And now we can execute on our conversion. So we're trying to go from 156 grams of C6H6 to the moles of C6H6. So then, if we have 156 grams and we want to convert to moles, we want to make sure that our conversion factor has the units of moles on top. So we know in 1 mole of C6H6, we have 78.06 grams. Punching this into our calculator, that in turn gives us 1.998 moles of C6H6 that we immediately round to 3 sig figs, which would be 2.00 moles of C6H6. Does this example make sense to everyone? Does this example make sense? Any questions on this example? Don't be shy to ask your questions verbally or in the chat, and I'd be happy to get them addressed. Okay. Yes, please go ahead.
I mean, it's just a small question, but like, say for instance, on my lab manual, my hydrogen is 1.008. So
yes.
in my head, I would round it to 1.01. Is that for later problems going to have any issues? Because like right now I got the same answer.
It will, as long as you're, so for each exam or assignment, you'll be given a periodic table. The periodic table sometimes are rounded to a different number of decimal places.
Okay.
As long as you use the atomic masses directly from the periodic table, for example, attached to your exam, provided by your lab manual, the atomic masses are almost identical in all
Okay.
the it's just the number of decimal places that are reported and the precision that each of these atomic masses are reported to.
Okay.
And in general, you just write out the full atomic mass in whatever periodic table reference that you're using.
All right,
And
perfect. Thank you.
usually the problems I'm mainly looking for in these problems that you're pulling the right atomic mass and that you're putting together the molar mass in this unit conversion correctly. If there's a small difference in the final answer, that would often be corrected once you round to the right number of sig figs. But that's a very good question to keep in mind.
Awesome. Thank you.
So let's keep going now, and let's look at a somewhat more difficult example. So I'm going to do the first one, and you'll handle the second one. We're asked, what is the mass in grams of calcium phosphate for a 3.2 mole sample? So we're trying to go from moles of calcium phosphate to grams of calcium phosphate. So in order to tackle this problem, I need to get my formula. And in order to get my formula, I need to use my name. So calcium phosphate. So we have calcium 2+, that because this is an ionic compound. What is phosphate? Would someone like, what is the formula for phosphate?
PO4.
Yep. Phosphate is PO4 3 minus. And now that we have each of our ions, to get the formula, we simply cross each of our charges into the subscript. So that gives us calcium 3, PO4 2. Now, with this information in mind, we can calculate the molar mass of calcium phosphate. So we take the mass of calcium, which is about 40.0 gram per mole of calcium, and we have 3 calcium atoms, plus the molar mass of phosphorus, which is 31.0 gram per mole of phosphorus, and we have 2 phosphorus atoms. Then we take 16.0 gram per mole of oxygen and we multiply by 8 oxygen atoms. Punching this into our calculator, that in turn gives us a molar mass of 310.0 gram per mole. Is everyone able to hear me okay? Are there any issues with the Zoom call stream so far?
I hear you okay.
Okay, perfect. If there are any issues with the stream, just let me know and I'll be happy to try my best to correct any of those issues. So now that we have our molar mass, to go from moles to grams. So if we have 3.2 moles of calcium phosphate, to go from moles of calcium phosphate to grams of calcium phosphate, we're going to use our molar mass. To go from moles to grams, we're going to want grams on top. So we plug in 310 gram per mole of calcium phosphate. The moles cancel, and in turn, we are left with a final mass of 992 grams of calcium phosphate, which we round to 990 grams of calcium phosphate to respect that our input had only 2 significant figures. Does this example make sense? The only thing that's new here is that you have to apply your previous nomenclature skills towards solving and figuring out the formula of your compound. Does that make sense?
Professor, I have a question about the atomic mass you're using. So when
Sure.
you're reading from the table, is it okay to round them up? Like, for example, for phosphorus, I noticed you just put 31 instead of 30.97.
The periodic table that I'm using has the atomic masses truncated to only 1 decimal place. You'd write out the full atomic mass in your provided periodic table. I'm just using one that only has 1 decimal place, so that way everything fits into 1 line and it's a little bit cleaner to look at.
So for the exam, for example, we are doing, the number wouldn't be changed, wouldn't be different than your answer keys?
The number would be within the margin of error.
Okay,
And
got it. Thank you.
in terms of your molar mass calculation, as long as your calculations are clearly shown, I can check them and provide credit.
Okay.
And I will make sure for every exam, you'll receive a copy of the periodic table that I want you to use for that exam.
Okay. Makes sense. Thank you.
Perfect. So to test that we're comfortable with this kind of problem, let's look at this next example. And I'd like you to calculate how many moles of lithium sulfate, are found in 165 grams of lithium sulfate. So we'll work on this problem over the course of about 5 to 6 minutes. But what I'd like from everyone, just to start us off, is I'd like everyone to think about the formula for lithium sulfate. And I'd like to see some proposals in the chat or verbally for the formula of lithium sulfate.
Lithium 2SO4.
Yep, exactly right. Just to explain the logic behind that, lithium adopts a +1 charge because it's a 1A element. Sulfate is SO4 2-. We cross our charges and that gives us lithium sulfate. So now that we've crossed this first bridge of figuring out the formula, we're able now to treat this problem as a typical mass to mole conversion. We calculate the molecular mass or the molar mass, and then we use the molar mass to calculate the moles of our sample. So let's work on this example. Let's spend about 4 to 5 minutes on this example, and let's try to see some proposals in the chat for the moles of lithium sulfate present in this sample. You can also message in the chat or share verbally the proposed molecular mass or molar mass of lithium sulfate. Anything that would be helpful to check your work and your progress in solving this problem, I'd be happy to provide feedback. And again, don't be shy to share your proposed responses in the chat or verbally. And we'll discuss this example in about another 3 minutes. Everyone's quite fast at this, actually. It's really great to see. But we'll make sure to give the entire class a little bit more time, so that way they can propose their response. This type of question is pretty likely to show up on the next exam, and this is really the fundamental process that you'd need in order to solve more complicated problems. And if you have any questions working through these examples, don't be shy to ask them verbally or in the chat, and we'll discuss in about a minute to a minute and a half. Okay, so let's look at this example. So first we need to calculate the molar mass of lithium sulfate. So we have 7.00 gram per mole of lithium, and we have 2 lithium atoms in our formula. We have a mass of 32.0 gram per mole of sulfur, and we have 1 sulfur atom. And we have 16.0 gram per mole of oxygen, and we have 4 oxygen atoms. That gives us, for our molar mass of lithium sulfate, then, we have 7 times 2 plus 32 plus 16 times 4. That in turn gives us a molar mass of 110.0 gram per mole of lithium sulfate. Now that we have our molar mass, we're asked to go from the grams of lithium sulfate to the moles of lithium sulfate. And for that, we'll use our molar mass. So given that our initial mass is 165 grams of lithium sulfate, if we wanted to go from grams to moles, we would use our molar mass. In 1 mole of lithium sulfate, we have 110.0 grams. The units of grams cancel, and punching this into our calculator, we in turn get 1.50 moles of lithium sulfate. Does this make sense to everyone? Is everyone comfortable with this example? Any questions on this example? Okay, so let's keep going with this. So we're next going to talk about atom to mole and molecule to mole conversions. So we've already established to go from moles to mass, we use our molar mass. To go from moles to mass, we multiply by our molar mass. To go from mass to moles, we divide by our molar mass. Well, how do we go from moles to atoms or molecules? With that, we use Avogadro's number. To go from moles to atoms or molecules, you're going to multiply by Avogadro's number. Conversely, if we wanted to go from atoms or molecules to moles, we're going to divide by Avogadro's number. Now, let's talk a little bit about what Avogadro's number is doing. For atomic species, Avogadro's number allows us to convert from moles to atoms, where Avogadro's number is 6.02 times 10 to the 23rd. In other words, in a mole of atoms, we have 6.02 times 10 to the 23rd atoms. Now, for a molecular species, Avogadro's number allows us to convert from moles to molecules or formula units. A mole of molecules is 6.02 times 10 to the 23rd molecules. Okay, so let's look at this in practice. So for example, we're asked how many moles of lithium are there in 2.0 times 10 to the 22nd atoms of lithium. So we're starting off with units of atoms of lithium, and we're trying to go to moles of lithium. So we have 2.0 times 10 to the 22nd atoms of lithium. And my question to all of you is, what units should be on top in this conversion? If we're going from atoms to moles, what units should be on top?
Moles.
Yep. So in 1 mole of lithium, we in turn have 6.02 times 10 to the 23rd atoms of lithium. So punching this into our calculator, we have 2.0 EE22. And now it's really important in your calculator, enter Avogadro's number in parentheses. Otherwise, your order of magnitude will not be correct. So we hit the division symbol. So we'd enter this into your calculator as 2.0 EE22. And then you're going to hit the division symbol, parentheses 6.02 EE23. If you enter it exactly the way I've written it down here, and you push each of these buttons in your calculator in this order, you won't have any rounding errors. So if we divide by parentheses 6.02 EE23, that gives us, for our moles of lithium, 0.033 moles of lithium. And I highly encourage you to try entering this into your calculator just to make sure that you're comfortable executing these calculations and using your calculator to complete mass to mole calculations. Does this make sense to everyone? Does this make sense to everyone? Okay, so we saw a nice reasonable pool of responses as we work through this problem. Let's now check our understanding, and I'd like you to work on the following 2 examples. In the first case, we're calculating the moles of sulfur given the atoms of sulfur. And in the second example, you're calculating functionally the molecules of sodium carbonate given the moles of sodium carbonate. So let's take about 4 to 5 minutes to work through these examples, and then we'll come together as a group to discuss. And if you have any questions, don't be shy to ask those questions verbally or in the chat. And don't be shy to share your proposed responses in the chat or any questions that you have in the chat or verbally, and I'd be happy to provide feedback. You can also share your responses and work for the problem using the annotate feature on our class whiteboard.
Professor, I have a question about the atom to moles.
Yes.
So, since we are just using one conversion, we say 1 mole to 6.02 times 10 beta 1 to 23, right?
Yep.
10 to 23.
Yep.
So my question now is this. So that 1.2, for example, in this question for the sulfurous. So it's going to be like if we have this amount, this many atoms, so it should be the same for any other elements since we are not using any
Yes,
specific.
yes, exactly.
Oh, okay.
They
So
should be
instead
different.
of like whatever answer we get right now for sulfurous, if we change sulfurous, let's say to lithium, it's going to be the same amount of moles for lithium, right?
Yes, exactly right. Because
Oh, got it.
moles are just a universal unit of counting large numbers and large groups of atoms or molecules. Exactly right.
Oh, got it. Okay, thank you.
Mhm. So let's keep working through these examples and we'll discuss in about 3 minutes.
What is the formula units?
So formula units is a term that describes ionic compounds, and it describes the smallest ratio of ions in the ionic compound. Formula units practically has this is functionally equivalent to saying the molecules of sodium carbonate. And we talked about formula units in chapter 2 of the notes. It's essentially describing the simplest molecular formula of an ionic compound. You can treat it just like molecules for the purposes of calculations and for the purposes of atom to mole and molecule to mole conversions. Does that make sense?
Yes.
Perfect. So let's keep working through this example and we'll discuss in about another minute and a half. And let's continue fielding responses in the chat and we'll discuss in about another minute. And it's great that we see a reasonable pool of responses in the chat. Let's try to get a few more responses to round out our discussion. And don't be shy to share your response, even if it differs from your classmates.
So Professor, when it says calculate the formula units, it's asking us to do what? Like how many moles?
So formula unit, you can think of it as the simplest. A formula unit is very similar to the number of molecules of an ionic compound. Formula unit is just used specifically when we're describing ionic compounds. So when you read the word formula unit from a calculation perspective, treat it just like molecules. Does that make sense? And just like we can use moles to go, just like we can use Avogadro's number to go from moles to atoms, we can use Avogadro's number to go from moles to molecules or moles to formula units. It's all the same
Same
process.
thing.
Does that make sense?
Yes, so it's basically asking calculate the molecule moles of this, right? That's what it is.
Calculate the molecules of
Moles.
sodium carbonate. Exactly.
All right, thank you.
Mhm. So let's discuss these examples. Let's discuss this first example. So we are given the atoms of sulfur and we're asked to calculate the moles of sulfur. So if we have 1.2 times 10 to the 24th atoms of sulfur, to go from atoms to moles, we're going to want units of moles on top. And we know that in 1 mole of sulfur, we have 6.02 times 10 to the 23rd atoms of sulfur. Again, punching this into our calculator. Remember, you enter Avogadro's number in parentheses. You don't want to introduce rounding errors and you don't want to end up with your calculator giving you the wrong output. And punching this into our calculator, this gives us 2.0 moles of sulfur. Does this first example make sense to everyone? Any questions on this first example? Okay. We saw a nice reasonable pool of responses in the chat for these questions. So let's look at this next part. In this case, we're asked to calculate the formula units of sodium carbonate in 1.29 moles of sodium carbonate. So we're going from the moles of sodium carbonate to the formula units of sodium carbonate. Okay, if we have 1.29 moles of sodium carbonate, we know that in our conversion, if we're going to formula units, we're going to have formula units on top. And we know that there are 6.02 times 10 to the 23rd formula units per 1 mole of sodium carbonate. Punching this into our calculator, that in turn gives us 7.765 times 10 to the 23rd formula units of sodium carbonate, which we in turn round to 7.77 times 10 to the 23rd formula units of sodium carbonate. Does this example make sense to everyone? Is everyone comfortable with this example? Any questions before we move on to another set of examples and another concept in this chapter? So let's keep going then. And let's just really make sure that we're comfortable with this idea. So I'd like you, now that we've seen our first representative example, I'd like you now to spend about 4 to 5 minutes and complete the following 2 problem solving examples where we're asked to calculate the atoms of nitrogen per mole of nitrogen and the moles of aluminum oxide per a given number of molecules of aluminum oxide. So let's work on this example. Let's really make sure we're comfortable with atom to mole conversions. And then we'll discuss this example in about 4 to 5 minutes. And if you have any questions, of course, don't be shy to message in the chat. And it's nice to see that we have a pool of responses in the chat. Don't be shy as well to contribute responses verbally or in the chat. And we'll discuss this example in about another 2.5 to 3 minutes. Practice makes perfect. And if you have any questions working through these examples, don't be shy to ask. And if there are any questions, it's great to see that students are working through these problems and then sharing their solutions in the chat. If there are any questions as well that you have, don't be shy to ask them in the chat or verbally. And we'll discuss this example in about another minute to a minute and a half.
Professor, for the rounding rule, so
Yes,
when I calculated, I'm talking about the second question.
yes,
So calculator give me 0.5. And I know the number we have, it has 3 sig figs. Should I add 0, 0 to make it 3
yes,
sig figs?
exactly right.
Good. Okay.
Exactly right.
I got it. Thank you.
So on that note, let's discuss this example. So we're asked to calculate the atoms of nitrogen in 0.25 moles of nitrogen. So we're trying to go from moles of nitrogen to atoms of nitrogen. So we'll use Avogadro's number. So with 0.25 moles of nitrogen, we know that we have 6.02 times 10 to the 23rd atoms of nitrogen in 1 mole of nitrogen. Punching this into our calculator, that in turn gives us 1.5 times 10 to the 23rd atoms of nitrogen. Any questions on this first example? Any questions on this first example? Okay, so let's keep going now. Next, we're asked to calculate the moles of aluminum oxide given the molecules. So we're trying to go from the molecules of aluminum oxide to the moles of aluminum oxide. So given that we have 3.01 times 10 to the 23rd molecules of aluminum oxide, we know that in 1 mole of aluminum oxide, we have 6.02 times 10 to the 23rd molecules. And punching that into our calculator, that in turn gives us 0.500 because our input has 3 sig figs, our output needs 3 sig figs, moles of aluminum oxide. Does this example make sense to everyone so far? Does this example make sense? Any questions on this set of atom to mole and molecule to mole conversions? Okay, so let's add a little bit of complexity to this and let's link our mass to mole and our atom to mole conversions together. So in this case, we can use the molar mass or atomic mass along with Avogadro's number to calculate the atoms of an element in a sample of that element. So we're starting to add a few steps to this process. So for example, we're asked how many atoms of iron are in 33 grams of iron. So we're trying to go from grams of iron all the way to atoms of iron. And where do we get the atoms from? How do we calculate atoms? What is our intermediate unit? What unit allows us to calculate atoms? What unit allows us to calculate atoms?
AMU,
You can go to AMU. What other unit?
Would it be moles?
mole,
Moles. Yep, exactly right. And we're going to go through moles because it's easier to go from grams to moles. That's a one-step conversion. So with this established, if we look up iron in the periodic table, what is iron's molar mass? What is iron's molar mass?
55.85.
Perfect. Wonderful. So to go from grams to moles, we'll use our molar mass. And to go from moles to atoms, we'll use Avogadro's number. So in our first step, if we have 33.0 grams of iron, we're going from grams to moles. So then we need units of moles on top. We know in 1 mole of iron, we have 55.85 grams of iron. The units of grams cancel. We're now ready to execute the next part of our conversion to go from moles of iron to atoms of iron. So then, in this case, what unit should go on top? What unit should go on top? If we're going from moles to atoms, yes, we want atoms on top. Exactly right. So we have 6.02 times 10 to the 23rd atoms of iron in 1 mole of iron. Moles cancel. And now punching this into our calculator, we have 33.0 over 55.85 times 6.02 EE23. That in turn gives us 3.557 times 10 to the 23rd that we round to 3.56 times 10 to the 23rd atoms of iron. Does this first example make sense? Does this first example make sense? We went from grams to moles, then from moles to atoms. So we're essentially taking the two parts that we discussed earlier on in this lecture and combine them together. Does that make sense?
Yes.
Okay, so let's look at another case where we're asked to calculate the mass in grams of a number of molecules of calcium hydroxide. So in this case, we're starting off with molecules of calcium hydroxide. And in the end goal, we want to calculate the grams of calcium hydroxide. Now, what is our stepping stone in this case? What is our intermediate unit in this case?
Moles per molecules.
Yep. So we're trying to go through the intermediate unit of moles. Yep, exactly right. So just like before, in order to go from molecules to mole, we're going to use Avogadro's number. And to go from moles to grams, we're going to use our molar mass. So let's calculate the molar mass of calcium hydroxide. So we take the mass of calcium, which is 40.0 gram per mole. We have 1 calcium atom. plus the mass of oxygen, which is 16.0 gram per mole. And we know in this case, we have 2 oxygen atoms. Then we take our mass of hydrogen, which is 1.00 gram per mole, and we know that we have 2 hydrogens. That gives us a molar mass of calcium hydroxide of 40 plus 32 plus 2 of 74 grams per mole of calcium hydroxide. Perfect. So now we have all the pieces that we need to execute on this problem. So if we want to go from molecules to moles, we write out our molecules. And we know that if we're going from molecules to moles, we want units of moles on top. So in 1 mole of calcium hydroxide, we have 6.02 times 10 to the 23rd molecules of calcium hydroxide. Next, if we wanted to go from moles to grams, we can in turn utilize our molar mass, which is 74 grams per 1 mole of calcium hydroxide. Punching this into our calculator gives us a final result Remember, enter Avogadro's number in parentheses. After punching this into our calculator, we get 1.86 grams of calcium hydroxide. Does this question make sense to everyone? So we started off from molecules. We went from molecules to moles using Avogadro's number, more specifically by dividing by Avogadro's number. Then we went from moles to grams by multiplying by the molar mass. Does this make sense? Does this problem-solving process make sense to everyone so far?
Yes.
Okay, so let's apply what we've learned and let's deal with and let's work on some atom to mole and molecule to gram conversions. So let's work on these 2 multi-step conversions. I'll give everyone about 5 to 6 minutes to work through these examples. And I'd like you to share any questions or responses that you have in the chat or verbally, and I'd be happy to provide feedback. Practice makes perfect, and independently and working on these problems together as a class and going through the process of writing down the conversion factors and working through the calculations is really invaluable to developing the same skills that you'll apply on your exams. So let's spend about 5 to 6 minutes on this example, and then we'll discuss. And again, don't be shy to share your responses in the chat. I'd like to see a pool of responses for both of these questions before we discuss. And if you need more time on any of these problems, really don't be shy to let me know. The more input and more feedback I get back in terms of how you're working through these problems and your proposed solutions to these problems, the more I can fine tune the amount of time provided and fine tune how we work through these problems. And let's keep working through these examples. I greatly appreciate the pool of responses that we see so far. And we'll discuss in another 2.5 to 3 minutes. So the best way to figure out how to start these problems is to write your starting units and your final units. And then once you have your starting and final units, you decide what intermediate unit, what stepping stone will get me between these two units. Once you have your unit map created, then you use your conversion factors to go from one unit to another. Did that answer your question about how to start off these problems? So write out whatever units you're starting out with, then write out what units you want to end at, and then think, how do I go between these units? What intermediate stepping stone will I have to go through? And most of the time, you're going to be going through moles overwhelmingly in the majority of these examples. Did that address your question? Perfect. So let's keep working on this example for another approximately 2 minutes, and then we'll discuss.
Professor, we are working just on the sodium right now, right? Or there's one more.
Yes, you can also work on the mercury oxide example as well if you finish the first example. We're working on this pair during this time, and any responses that I receive, I'd be happy to provide feedback on.
But
Does
could
that
you
make
go
sense?
down a little bit? I can see the next one.
Certainly. There we go.
Okay,
Is that
thank you.
better?
All right, thank you. Yes, much better. Thank you.
Perfect. And we'll discuss this example in about another 1.5 to 2 minutes. It's great to see that we have, as we continue on with the session, more and more students starting to contribute in the chat and share their responses. And they all look great so far. So let's keep up the effort, and we'll discuss in another 1 to 1.5 minutes. Okay, so let's discuss this example. So for sodium, we're starting off with the atoms of sodium, and we're trying to calculate the grams of sodium. What intermediate stepping stone, what intermediate unit will we be going through? What unit gets us from atoms to grams? Yep, moles. So we're going to go through moles of sodium. Looking up sodium in the periodic table as has an atomic mass of roughly 23.0 gram per mole. So now that we have all of our now that we have all of our units in place, we'll delineate and we'll specify our conversion factors. So to go from atoms to moles, we're going to use Avogadro's number. And to go from moles to grams, we're going to use our molar mass. So if we have 8.6 times 10 to the 22nd atoms of sodium, we know to go from atoms to moles, we're going to want units of moles on top. And we know in 1 mole of sodium atoms, we have 6.02 times 10 to the 23rd atoms. Additionally, now that we've completed the first step, to go from moles to grams, we'll use our molar mass, which is 23.0 gram per mole of sodium. Now, punching this into our calculator gives us we get 3.3 grams of sodium. Any questions on this first example? Any questions on this first example?
Professor, how when we're doing it in the calculator,
Yeah.
we go ahead and use that same formula that we had put, previously, as far as like how we enter the EE.
Yep, so we'd enter, so if you're entering this into your calculator, you'd enter 8.6, then you'd hit the EE button, then enter 22. Then you'd hit the division symbol, followed by parentheses, and then 6.02 EE23. And then once this first part is processed, then so you'd hit the equal symbol, and then you'd hit the multiplication symbol and enter 23.0, and then you'd hit the equal symbol once again.
Okay, I got it. Would there be a problem if would it be a different answer if we didn't enter the parentheses?
Yes, because essentially if you don't enter the parentheses, some calculators, they don't group the number and the power of 10 together. So I just always enter Avogadro's number in parentheses just to ensure consistency and to avoid calculator errors.
Okay.
If you notice that the number is really large or really small, that's usually a bad sign. And likely a sign that there was a calculation error.
Okay, thank you.
Perfect. Any other questions on this first portion? So let's keep going now, and let's look at the next example where we're asked to calculate the molecules of mercury oxide in 200 grams of mercury oxide. So my first order of business in this problem is I'm going to figure out the molar mass of mercury oxide. Would someone like to volunteer and tell me what is the atomic mass of mercury? What is the atomic mass of mercury in the periodic table? What is the mass of mercury?
200.6.
Perfect, perfect. So we have 200.6 grams per mole of mercury, and we have 1 mercury atom. And then for oxygen, it's 16.0 gram per mole of oxygen, and we have 1 oxygen atom. That gives us 216.6 grams per mole of mercury oxide. Okay. So continuing on, now that we have the molar mass, let's write out our units and let's figure out what conversion we need. So we're starting off with the grams of mercury oxide. And in the end, we want to figure out the molecules of mercury oxide. So what intermediate stepping stone will we use?
Moles.
Yep, exactly right. So once we have that established, we're now going to figure out what conversion factors we need. So to go from grams to moles, we're going to use our molar mass. And to go from moles of mercury oxide to molecules, we're going to use Avogadro's number. So then let's execute on that. So if we have 200 grams of mercury oxide, to go from grams to moles, we're going to want units of moles on top. And in 1 mole of mercury oxide, we have 216.6 grams. To go from moles to molecules, we know that we have 6.02 times 10 to the 23rd molecules of mercury oxide in 1 mole. So punching this into our calculator, we have 200 over 216.6 times 6.02 EE23, and that in turn gives us 5.5586 times 10 to the 23rd molecules of mercury oxide that we round to 6 times 10 to the 23rd molecules of mercury oxide. Does this question make sense? Does this process of multi-step conversions make sense to everyone? Does this make sense to everyone so far? Perfect. So let's look at some examples where we have to deal with nomenclature. So we're given the name of a compound and we're asked to calculate formula units, moles, etc. So let's look at this example. In this case, we're asked to calculate the formula units of potassium sulfite present in 20.3 grams of potassium sulfite. So our first order of business is to figure out, the formula. So potassium sulfite. Does anyone have a proposed formula for potassium sulfite?
K2SO3.
Yep. So potassium is potassium plus or K plus. Sulfite is SO3 2 minus. We cross our charges and that gives us K2SO3. Now, we're going to calculate the molar mass of this sample. So in this case, to calculate the molar mass, we add up the mass of each atom in our sample. So potassium is 31.0 gram per mole. And we know that we have 2 potassium atoms. So, oh, sorry.
Potassium is 39.
Sorry about that. Yes, that's exactly right. Double checking in the periodic table for potassium. Yep, 39 gram per mole. And we have 2 potassium atoms. Sulfur is 32.0 gram per mole, and we have 1 sulfur atom. And oxygen is 16.0 gram per mole, and we have 3 oxygen atoms. So punching this into our calculator, this gives us a molar mass of, so we have 39 times 2 plus 32 plus 16 times 3. That gives us a molar mass of 158.0 gram per mole. Okay, so now that we have this molar mass figured out, let's look at what we're being asked to do in the problem. So we're asked to go from the grams of potassium sulfite to the formula units, which you can think of formula units exactly the same as molecules. So what is our intermediate unit once again? What is our intermediate
Mole.
unit? Moles, yep. So now that we have our solution map set up, we know that we're going to go from grams to moles using our molar mass, and we're going to go from moles to formula units using Avogadro's number. Now that we have this set up, we're going to execute on this. So, starting off with 20.3 grams of potassium sulfite, we know that in 1 mole of potassium sulfite, we have 158.0 grams. We just calculated that. To go from moles to formula units, we know that we have 6.02 times 10 to the 23rd formula units of potassium sulfite in 1 mole of potassium sulfite. That in turn gives us 7.73 times 10 to the 22nd formula units of potassium sulfite. Does that make sense to everyone?
Yes.
Perfect. So to test that everyone's comfortable with these examples that integrate nomenclature and multi-step conversions, I'd like you now to work on the following example. And I'd like you to calculate the mass in grams given the molecules of phosphorus pentachloride. And we'll work on this example for about 3 to 4 minutes. And I'd like to see some responses in the chat for their proposed solutions. And if there are any questions working through this example, don't be shy to ask. Our first order of business before we really delve into this problem is getting the formula for phosphorus pentachloride. And if anyone would like to share the proposed formula in the chat, that would be extremely helpful. Yep, so from covalent compound nomenclature, phosphorus pentachloride, we have phosphorus, pent 5, So we have 5 chlorine atoms. So phosphorus pentachloride has the formula of PCl5. If you're stuck on the name and writing the formula from the name, make sure to review the chapter on nomenclature. So let's keep working on this example and we'll discuss in about another 3 minutes. And don't be shy to share any questions you have or your proposed responses in the chat or verbally. And we'll discuss this example in another 1.5 to 2 minutes. And it's nice to see that we're starting to see a pool of responses in the chat. That's really helpful to see, as it helps me get a sense of how students are working through this problem. Let's try to get a few more responses and we'll discuss in another approximately 1 minute. Okay, so let's discuss this example. So first things first, given the formula, let's calculate the molar mass of phosphorus pentachloride. We know that phosphorus has a mass of 31 gram per mole, and we have 1 phosphorus atom. Chlorine has a mass of 35.5 gram per mole, and we have 5 chlorine atoms. Punching that into our calculator, we have 31 plus 35.5 times 5, and that gives us a molar mass of 208.5 grams per mole of phosphorus pentachloride. Now that we have our molar mass calculated, let's look at what we're being asked to do in the problem. So we have the molecules of phosphorus pentachloride, and we're trying to calculate the grams of phosphorus pentachloride. What is our stepping stone? What intermediate units are we going through?
Moles.
Yep, exactly right. Now that we have this established, now that we have this set up and ready to go, what we're going to do is we're going to execute on this conversion. So given that we have 4.63 times 10 to the 22nd molecules of phosphorus pentachloride, to go from molecules to moles, we use what conversion factor? What conversion factor gets us from molecules to moles? How do we go from molecules to moles? What conversion factor?
Mole per molecules.
Yep, So, and in that case, we're going to be using Avogadro's number, where in 1 mole of phosphorus pentachloride, we have 6.02 times 10 to the 23rd molecules. Next, to go from moles to grams, we're going to use our molar mass, which we established was 208.5 grams per mole of phosphorus pentachloride. Now, punching this into our calculator, that we get 4.63 EE22 over 6.02 EE23 times 208.5, and that gives us 16.0 grams of phosphorus pentachloride. Does this example make sense to everyone? Does this example make sense?
Yes.
Perfect. So let's talk a little bit about the chemical formula. So the chemical formula is a really useful tool as it provides a relationship between the moles of a molecule and the moles of the atoms of an element in that molecule. Additionally, the chemical formula also allows you to relate the moles of one element in a compound with the moles of another element in a compound. Now, the conversion factor that we derive from the chemical formula is known as the formula ratio. It's the ratio of the moles of an element to the moles of a compound. Or another version of the formula ratio is the ratio of the atoms of one element in a compound to the moles of another element in that compound. Okay, so let's look at an example. So for N2O5, how many nitrogens do we have in N2O5? How many nitrogens do we see? Let's draw a picture. I find when in doubt, you might as well just draw a picture. Okay, so how many moles of nitrogen do we have? How many moles of nitrogen? 2. So we have 2 moles of nitrogen per mole of N2O5. So in 1 mole of N2O5, I see 2 nitrogens. Okay, what about oxygen?
Five.
Yep, exactly right. We have 5 moles of oxygen per mole of N2O5. Now, just like we can look at the ratio of moles of an atom to moles of a molecule, we can also, in turn, look at the ratio of the moles of one element to another. So we can also say that we have 2 moles of nitrogen per 5 moles of oxygen. Now, in addition, we can also write this ratio as a ratio of atoms. So these are our mole to mole ratios, but we can just as easily say we have 2 atoms of nitrogen per 1 molecule of N2O5. So we can just as easily write these ratios in terms of atom ratios. Does that make sense to everyone? Does everyone see how we can read the formula and develop some conversion factors that relate the moles of a molecule to the moles of an element in that molecule? Does that make sense?
So Professor, mole is the same as atom?
So the mole ratio is the same as the atom ratio.
Okay, the ratio. Okay, got it. Thank you.
So let's look at an example now. We're asked to calculate how many moles of nitrogen are there in 13.5 moles of N2O5. So we're trying to go from the moles of N2O5 to the moles of nitrogen. So given that we have 13.5 moles of N2O5, looking at our conversion factor, what units need to be on top? What units need to be on top? The moles of what needs to be on top? If we're going from moles of N2O5 to the moles of nitrogen, we want the moles of nitrogen on top and the moles of N2O5 on the bottom. And we see from our formula, we have 2 moles of nitrogen per every 1 mole of N2O5. And that would give us 27.0 moles of nitrogen. Does this make sense? Does everyone see how we can utilize our formula ratio? Let's look at another example. This time we're asked to calculate how many moles of nitrogen are in a sample of N2O5 containing 4 moles of oxygen. So in this case, we're asked to go from moles of oxygen to moles of nitrogen. So given that we have 4.0 moles of oxygen, if we're going from moles of oxygen to moles of nitrogen, what unit needs to be on top? What unit needs to be on top?
Nitrogen.
Yep, exactly right. And moles of oxygen needs to be on the bottom. So how many moles of nitrogen do we have per oxygen? What's our formula ratio?
2.
Exactly right. We have 2 moles of nitrogen. We see 2 nitrogens here per every 5 moles of oxygen. Punching that into our calculator, we have 4 times 2 over 5, which gives us 1.6 moles of nitrogen. Does this example make sense to everyone? Does this example make sense?
How did you do the calculation again?
So if we're going from moles of oxygen to moles of nitrogen, we write out our starting units, which is moles of oxygen, and looking at our formula, the ratio of atoms gives us the mole ratio of each element. So in this formula, we have 2 moles of nitrogen per 5 moles of oxygen. 2 nitrogens, 5 oxygens. That conversion factor allows us to convert from the moles of oxygen in our sample to the moles of nitrogen.
How many moles of nitrogen are in this containing 4 moles of oxygen? Okay, so mole of oxygen, you're gonna go to mole of nitrogen.
Does this make sense to everyone? Any other questions that I can address?
Yes, my question was when you calculated the answer, you multiplied the 4.0 moles to 2.
Yes, we multiply it by the ratio of 2 over 5 because for every,
Okay.
we have 2 moles of nitrogen in our formula per every 5 moles of oxygen.
So we multiply by 2.
So you take 4 times 2 divided by 5.
Okay, got it. Thank you.
Perfect. So this is a great stopping point for today. I'd like you to review these examples. And just to give you a little bit of context here, this process, this is really building up towards later on in this class when we calculate pH, when we calculate concentration, when we talk about preparing solutions, when we talk about preparing formulations with defined mass percentages, all of these fundamental conversions that we're doing are building towards the skill set that you need as part of your nursing classes, where you're thinking about solution prep, formulation prep, calculating concentration, calculating pH, figuring out how to dispense and prepare samples with a defined composition. All of these skills are built upon this backbone of unit conversions and mass to mole conversions, because fundamentally, when you think about a sample of medicine, the important thing is not the mass of the sample, but how many molecules, how many moles are present in that sample, because it fundamentally, medicines function at a molecular level. We're looking at how that molecule interacts with other molecules in the body. So in order to figure out and calculate appropriate dosages, to figure out and calculate the appropriate concentration, we need to have these mass to mole conversions really solid. Does that make sense? So I know it seems like this looks a little different than this seems a little bit off from the practical stuff that I'd be doing as part of a nursing major, but this logic of unit conversions will serve you well in your later classes as part of your program. So with that established,